Hi everyone. So today we'll be discussing on the topic Steiner forest algorithm. So this is one of the famous or well-known optimization algorithms, right? So we'll be making use of the DP for this. So it's called as Steiner forest algorithm. Yeah. So what does the definition part says here? So the Steiner forest algorithm, what it finds the minimum cost subgraph. What it finds mainly, it finds the minimum cost subgraph that connects multiple groups of required vertices. What does it connect again? It connects multiple groups of required vertices called terminal sets. When I say terminal sets, it is nothing but the end vertices, right? End vertices at the molecular level. As we will be considering the graph, we can just say end vertices at the graph, right? The graph that we consider. So I'll get to know when we discuss the algorithm, right? So mainly with the graph, I'll be going with a simple example along with the graph. So you'll get to know that. So let's move on with the further things. The Steiner forest algorithm finds the minimum cost subgraph that connects multiple groups of the required vertices, also called as terminal sets in a graph. Unlike the Steiner tree, so there is an algorithm for the Steiner tree as well. So unlike the Steiner tree, which connects all the terminal. So when we haven't discussed the Steiner tree, I believe, right? So Steiner tree, what it does, it connects all the terminals, right? All the terminals in the sense, all the end vertices, right? So unlike the Steiner tree, which connects all the terminals, each terminal group must be connected only within its own group. So this is what it does. For the extreme optimization or the intense optimization, we'll be making use of this particular algorithm. Usually, it's called as Steiner forest algorithm. So we'll be having certain group of the terminal, a terminal, this one vertices or the terminals. Basically, that group it connects. Basically, that group it connects. Each terminal group must be connected only with its own group, minimizing the total edge cost. Minimizing the total edge cost, right? So this is it for the definition of the Steiner forest algorithm. Let's do one thing. Let's discuss the algorithm by considering the simple example, right? Let's do that quickly. So let's move on with the this one algorithm part. So we'll be going with this particular example graph. So first what we'll do, we'll consider the weighted graph. Just give me a second here. Yeah, we'll be considering the weighted graph. Weighted graph in the sense the edges will be having certain weights. Every edge will be having certain weight, right? So this is fine. So we are dealing with or we will be dealing with the undirected graph here. So we can just go with a directed graph as well, undirected graph as well. When it comes to the Steiner algorithm, it doesn't matter. So we are dealing with the undirected graph. For the example, I have considered the undirected graph. So let's consider this particular weighted graph here. So we have the edge A to B with a weight 1, we have the edge B to C with a weight 2, and we have the this one, what do we call, A to D with a weight 4 and B to E with a weight 3. So I can clearly see here terminal edges or the end edges, right? So the vertices, actually the vertex that is present at the end of the graph, A, D, E, and C. So this forms one group, actually A to C, right? You can clearly see here this forms one group. If I want to show in this way, so this forms one group. So I'll just write here first group or group A. So I'll just write here GA, nothing but group A. So this forms the second group. So these are the terminal this one edges as this is the terminal edge actually, which consists of the vertex D and vertex E, and this is group B or group 2. You can consider anyhow, right? So this concept is very simple. So we are considering the terminal edges or the terminal edge or the terminal vertex which forms its own group, right? So A, C, and D, E we have considered. Now terminal groups are, so group 1 and group 2, I have written group 1 and group 2. Group 1 is group A, group 2 is nothing but the group B. So it consists of AC. So terminal vertex is nothing but A and C, which are present at the end. So D and E for this particular group, you can clearly see here, right? It's as simple as that. Now let's move on with the further things. What is our main goal? Our main goal is to connect the nodes within each group with a minimum cost. So that's what we will be doing by making use of this particular algorithm, Steiner forest algorithm. So here we will be connecting the nodes within each group with the minimum cost. Again, we'll be connecting the nodes within each group with minimum cost, right? So the optimal connections, what are the optimal connections here? A, B, C, right? So this is the optimal connections from if we have to move from A to C, we have to consider A to B, then B to C, right? A to B is having the weight 1 and B to C we are having the weight 2. So that would lead to 1 plus 2, nothing but 3. 1 plus, sorry, not 1 plus, yeah, 1 plus 2, that leads to 3. Yep. Then we have another group, nothing but group 2 or group B. So where the edge is nothing but D and E, right? So we have already considered this one with the weight 1, with a weight 1. So here cost is nothing but 1, right? So the total Steiner forest cost would be this one. We'll be summing up this one and this one. 3 plus 1, that leads to 4. Yeah, the total Steiner forest cost is nothing but 3 plus 1, nothing but 4. So basically the algorithm, this particular algorithm, Steiner forest, this one, sorry, yeah, Steiner forest algorithm. So it essentially builds minimum connections for each terminal group. What it does, it essentially builds minimum connections for each terminal group, often using Kruskal or the Prim style, right? It often uses Kruskal or the Prim style MST, nothing but the minimum spanning tree logic with the union find. So Kruskal or the Prims. We have discussed this one. If you don't know, you can just go through the algorithm, this one 150 algorithms playlist. So it uses this one union find, right? Or the DSU, disjoint set union, right? So basically the algorithm essentially builds the minimum connections for each terminal group. So in our case, the example that we have considered, we went with a two terminal groups, right? Often using the Kruskal or Prim style MST logic with the union find. It's as simple as that. Yep. So this is fine, I believe. So this is it for the, what do we call, this is it for the algorithm. This is it for the Steiner, this one, what do we call, Steiner forest algorithm, right? So now we are done with the algorithmic part. Let's try to articulate the same thing in the form of code. Yeah, let's try to articulate the same thing in the form of code. If everything goes well, if we get the desired output, then we can discuss the complexities part. First, let's write the code. Let's try to articulate the same thing in the form of code. Let's do that. So let's do one thing. Let's move on with the further things here. So first thing, so we'll be making use of the different utilities. So I'll just import the utility package. So I'll just go with java.star, right? So this is not required. Anyways, let me remove this. Yeah, let's continue or let's move on with the further things. So within this, first thing before getting into this part, I'll be going with a class edge, right? So within the edge class, what I'll do, I'll consider vertices that we need, basically u and v with a weight, right? The graph comes with a weight as well. So I'll just go with u, v, nothing but the another vertex, and w. So this is fine. It's as simple as that. Now we need the constructor that initializes the edge and points in the weight. So I'll just go with the edge here. So this one will be in u, v as well as the w. So within the edge construct or the constructor part, so I'll just go with the this dot u equals u. So this is fine. This dot v equals v, and this dot w, nothing but the weight, equals w. Yep. This is nothing but the starting vertex, ending vertex, as well as the edge weight. So I'll just come out of this one entirely. Now, as I've said, so usually the Steiner forest algorithm makes use of the DSU, right? It usually it will be making use of the Prims or the Kruskal style, and it uses DSU. That's what we had discussed earlier. So let's go with the DSU. So I'll just go with the class DSU or the union find, however you call it. So within the DSU, first thing, I'll go with the parent, which is required. Yep. So first thing, let's go with the constructor as well. Yeah. Int n. So this is fine. Within the constructor part, so I'll just go with the parent. Let me go with new int of size, and it depends on the number of vertices. Yep. And also let me go with a for loop here for I equals 0, I less than n, I plus plus. Yeah. So parent of I, let me assign this one to the I. It's as simple as that. Now we have to go with the path compression, right? So I'll just come out of this one entirely. Yeah. This one, let me format the code so that the code looks good. Yeah. Next step is nothing but here we have to find the representative of the set with the path compression. Here in this case, let me go with the int find of int x. So this is fine. So within the find method, first thing, we are going with the path compression, right? So I'll just go with the if condition here. If parent of x, suppose if it is not equal to x, then parent of x is equivalent to find of parent of x. So this is nothing but yeah, as I've said, we are just compressing the path, nothing but path compression itself. Finally, we have to return the parent. So I'll just go with, we are just finding the parent actually. Yeah, through the path compression basically. I'll just return parent of X. It's as simple as that. If you know the this one DSU algorithm, so we are just trying to write the same thing right here. So we have written this one multiple times. We should be knowing at this point of time. We should be knowing this. Now let's go with this one union. Union method actually. I'll just go with void union. So let me go with the two parameters. One is A and another one is B. So here within the union, I'll just consider parent A. Yeah. So I'll just go with find of A here. So let me go with find of A, and in another one is parent B. So this one will be find of B. Yeah. So this is fine. Next what we are going to do. So I'll just go with a simple if condition. If PA not equal to PB, then within the if condition, I'll just go with a parent PB. Let me initialize this one to the PA. So this is it for the union, uh, union of two sets actually. Right. So we are done with the DSU part. Next, what shall we do? Let's move on with the main class. Actually, nothing but Steiner forest. So this one, diffuse Wagner. So this is not the one actually. Let me remove this one. So this is nothing but the Steiner forest algorithm. Yeah, I'll just do one thing. Let me change this one too. So let me copy the same thing here. So I'll just go with refactor here. Rename file. So let me change this one to this particular thing. Yep. Hit the refactor. Yeah, so this is fine. Within this particular class, I'll just go with a main method, right? So I'll just go with a public static void main. This is fine. Yeah, so this is not required yet. So let me do one thing. I'll just go with the number of vertices, the same example that we had considered while explaining the algorithm. So I'll just consider the same example, right? So the number of vertices we had was A, B, C, D, E, right? 5. So I'll just go with the number of vertices n, nothing but 5 here. So this is fine. We have to go with the edge list actually, right? So I'll just copy the edge list. Just give me a second here. So let me do one thing. I'll just come here and let me paste this one over here. So I'll just import this one array list. So we have made use of the this one, right? What is it importing actually? Oh, 1 second. I'll just go with the star here. Let me remove this one. Let me remove this one. Sorry. Yeah, this is not required. Anyways, yep. Let's move on with the further things. Yep. So these are the edges within the graph. I have already shown you the graph. Edges.add. So edges 0 to 1 with the weight 1, 1 to 2 with the weight 2, 0 to 3 with the weight 4, 1 to 3 with the weight 3, and this one 3 to 4 with the weight 1. You can just go to the video where we had discussed the algorithm actually. There I had shown you the graph. The same graph here we have represent the edges with the weight actually, right? A to B, B to C, A to D. This one. What do we call? Sorry. What did I do? Yeah, B to D as well as D to E. Yep. So this one I have already shown you. Next, let's go with the terminal groups. So we have already discussed this one. We had two terminal groups, nothing but A to C and D to E, right? So that one, A is nothing but 0 here. You can clearly see A is nothing but 0. B is 1. C is nothing but this one. What do we call? C is nothing but 2. D is nothing but 3. Yeah, E is nothing but 4, right? So D, yeah, D is nothing but 3, E is nothing but 4. Yep. So this is fine. We have just represented that one in the numbers. That's it. Yep. So there were two terminal groups A, C, and D, E, right? So here I'll just write it in this way. Groups equals. So I'll just go with A to C nothing but A is 0, C nothing but 2, and one more thing, D to E was the terminal group as well, right? So I'll just go with the 3 nothing but D, E nothing but 4, right? 4 nothing but E. Right, so this is fine. I'll just come out of this one entirely. We have to find the total cost itself. For that, I'll just go with the variable total cost. Let me initialize this one with a 0. The next step, so let's sort the edges by, let's sort edges by weight, nothing but the we'll be going with a Kruskal algorithm, kind of Kruskal, this one, what do we call idea, not entire and not entirely Kruskal's algorithm. It's kind of this one, we can say Kruskal's idea, right? So I'll just go with edges. Yeah, this one. So let me do one thing. I'll just go with a sort here. Yeah. despite sort, I'll just go with a comparator that is provided by the Java. So I'll just go with just comparator, or I'll just go with the comparator dot comparing what we have to compare. So instead of comparing, I'll just go with the comparing int, as we are dealing with the integers actually. So let me go with e. I'll just go with e dot w, nothing but the weight. So this is fine. It's completely fine. Initially, let me set the cost to 0. Yeah. So next, let's move on with the this one for loop, because we have to consider every edge that is present in the graph. Right. So I'll just go with the edge. So we have already written the edge class for the edges, right? So individual edge of edges. So within this for loop, I'll just go with the pu is equal to dsu dot find. Yep. So I'll just go with the e dot u. So this is fine. Let's do one thing. We haven't written the DSU part, right? So why this is showing error here? So I have written the DSU itself, right? 1 second. Oh, one mistake I have done after the total cost. Before sorting, actually, we have not considered the DSU at all, right? So that is the reason we have made use of the DSU based this one. Union by rank actually. So I'll just go with the DSU here equals new DSU this part of, let me include it's of size and 9. Anyways, yeah. Now the error should be gone. Yeah. So this is fine. And let me go with one more vertex, nothing but P, U and V, right? So this one will be PU and PV. So I'll just go with DSU dot find of this one E dot V. So this is fine. If connecting reduces the components, I'll just go with the if condition here. If PU not equal to PV, then I'll just go with a DSU dot union. So this one E dot DSU dot union. Here in this case, I'll just go with PU comma PV, right? So this is also fine. So let me go with cost equals cost plus E dot weight. Yeah, this one cost equals cost plus weight, right? So this is fine. I'll just come out of this one entirely. Now we have to stop if the terminals are already connected. For that, I'll just write one more if condition here. This will be simple. If DSU dot find this one, so we have to mention group. So this will be group of 0. Yeah. So 1 second. Group I haven't considered. Static constant, not this one actually. So let me do one thing. Here I haven't included this one also. I forgot actually. After total cost 0. So let me include one more for loop. So I got confused, I believe. Anyways, so I'll just go with let's consider individual group or this one, the terminal groups actually. In our case, we had two groups. We have to consider individual groups, right? So for that, let's go with a group of groups here. So let me open the this one bracket. Yeah, and one more thing, we'll just go with one more bracket here. So this is fine. So if DSU dot find, now the error is gone actually. So why this is showing error? Requested type boolean. So let's continue. Later we can debug actually. Group of 0. So this is fine. If it is equivalent to DSU dot find this one of group of 1. Yep, group of 1. Then we'll do one thing. So within this, I'll just go with a break here. So this is fine. Let me come out of this one entirely. Now, total cost, this one, total cost equals total cost plus cost. So this is also fine. So let me come out of this one entirely as well. So we are left with only one thing, nothing but we have to print something, right? So I'll just go with, we have to print the total cost itself. So so system out println. So let me include something within the string so that this looks good. Yeah. So let me give here minimum Steiner. Yeah. This one forest cost. So this is equivalent to uh this one less total cost. Yeah. So this is fine. Let me format the code so that the code looks good. Yep. So yeah, this looks good one. Yeah, we are not having any error, right? So now this error is also gone. Anyways, total cost, what it is showing here, reassign local variables. Reassigning the local variable is completely fine, not a problem. Yeah, this is it for the algo. Basically, we are making use of the DSU and crystal like this one structure, right? So for basically for relaxing the edges, right? So this is fine. That's it. The main thing is we will be going with a we have to consider the terminal groups, right? So this one, the normal algorithm directed a Steiner tree. It connects all the terminals, right? All the terminals. Instead here, it makes the groups of the terminals, and then it finds the this one total cost, right? That's the main difference between the directed what do we call directed Steiner tree and this one Steiner forest algorithm. Yep. So we are done with this particular algorithm. So let me format the code once and let's run the algo. So I'll just come here. So where is this part? Yeah. So let me run this one. Yeah. Here you can clearly see minimum Steiner forest cost is 6. Yeah. So we have to get the minimum Steiner tree. This one forest cost is 4, right? Accordingly, with the this one algorithm. Within the algorithm, we had considered the example. I had explained you with the example. There we got 4. We have to get 4 actually. So let me do one thing. We are considering unnecessary edge, I believe. So I forgot one if condition, or it's better to include this if condition, I believe. Let's do one thing. Just come here. Mm, yeah, let me paste this part over here. So yeah, we are just checking whether the edges are already connected, right? So if connected, we are just exiting, right? So we don't have to make use of that particular edge again, right? So let me rerun this one again. Still we are getting 6 itself. Let's see what's wrong we have done. So actually the answer 6 is correct. See why we are getting 6, why we are not getting 4, and why we are getting 6 is it's simple. As we are dealing with we should have went with the distance actually. If we went with the distance for the relaxation, it would have given us 4. So here we are making use of the crystal like structure. We went with the crystal like structures, and it uses this one, what do we call. So it is also including the extra edges that is unrelated to the this one terminals actually, as we are running the crystals, right? So it is also including unrelated edges from the terminal. So it is also including A2 A, B, C, we have considered D and D, right? So it is also including D. So in that case, we will be getting 6. So it might consider the unrelated edges as well, right? So as we are going with the crystals, right? This is not wrong. We can have the multiple outputs. This is also correct output itself, right? So we don't have to worry that much about it. Yep. So this is it for the algo, right? So this is it for the algo. Let's do one thing. Now we are done with the algorithm part. Let's solve or let's try to implement the same algorithm in one of the problems, right? Let's do that. So let's move on with the problem. Yeah. So here you can just search for UVA 1496. You can just go with the UVA website itself, or the JET. There only you can just submit, right? Or else you can just come to this one VJets, and you can just submit the UVA problems as well, right? It supports multiple judges. So usually I go with the VJets, right? It's easier, right? Interface is good. So this is fine. Yep. This is the problem actually. One second, just give me a second here. Yeah. So we have this PDF. So basically you have the download option here. You can just download the PDF, right? So I have already downloaded the PDF. So I'll just open the PDF. So this is the question actually. Yeah. You can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem. Let me do that. Just give me a second here. 1 second. Yeah. So first thing, there are n houses. Yeah. There are n houses connected by m broken roads. There are n houses. This n is nothing but houses. Yeah, there are n houses connected by m broken roads. Yeah, so connected by m. What are m actually? They are connected by m broken roads. Yep. So there are n houses connected by m broken roads with the repair cost W. Right. So with the repair cost W. Right. So K families lives in houses 1 to K. K families, what do? They live in houses from 1 to k. Actually, we have k families in simple terms, right? 1 2 3 4 up to k. K families lives in houses 1 to k. So k hiding houses exist at n minus k plus 1 to n. Actually, so we have hiding houses and k hiding houses. So I'll just write here k hiding houses. I'll just go with HH, nothing but the k hiding houses. So they exist at where do they exist? From n minus k plus 1 up to n. Actually, n minus 1, n minus k plus 1 up to n. Each can hide only one family, right? So this one, each can hide only one family. Just remember, this part is very important. Each can hide only one family. What we need to do here, we need to repair some roads so each family reaches a unique hiding house, right? So we need to repair some roads. We need to repair roads, right? So this one, m broken roads we have. So we need to repair what do we call some roads. So we need to repair some roads, or we need to repair roads here. So each family reaches a unique hiding house with a minimum total repair cost, right? So with minimum total repair cost. Yeah. So this is what we need to find actually. We need to find the minimum total repair cost. Yeah. So we have to repair some roads. So each family reaches a unique hiding house with minimum total repair cost. If it is impossible, then we have to print no solution. Suppose if it is impossible, then we have to print no solution. Just remember this. Yeah. So this is fine. This is it for the question actually. If it is impossible, in that case, we have to return no solution. Yep. So this is it for the coding part. Yep. Sorry, this is it for the question. Let me I read this one out loud again. Just listen to this. There are n houses connected by m. This one broken roads with a repair cost w. Right. So with the repair cost w. So k families live in houses from 1 to k. Right. So basically k families lives right from 1 to k, 1 2 3 4 up to k. This is fine. K hiding houses exist at n minus k plus 1 to n. So this one also I have written here. Only one condition here. The main condition is each can hide only one family at a time. Yep. So we have to repair some roads. So each family reaches a unique hiding house with a minimum total repair cost. Yeah. Minimum total repair cost which we have to find. So if it is impossible, in that case, we have to display no solution. Yeah, no solution. So this is the question actually. Yeah, this is the question. So let me delete this one entirely. Yeah, this is the question. So this is fine, I believe. So this is it for the question. We have to find is we have to find the total minimum cost. Yeah, total repair cost actually, minimum total repair cost. And if it is impossible, in that case, we have to display no solution. You can clearly see here for the first input they have given here sample input. So this one, we have two inputs that they have given. Yeah, we have two inputs here, right? So one is 2 4 3 1 4 to 10. So this one, this part up to here, and the second one starts from here. So this is fine. And for the first input we have to get the 29 as output, and for the second input we have to get the 5 as output, right? So this is it for the question, right? So I can just go through the questions within the you can just go through the this one constraints within the input as well as the output, which is very important. Yeah, t has to be less than or equal to 50, and n has to be greater than or equal to 4 and less than or equal to 50, and m has to be greater than or equal to 0 and less than or equal to 1000. They have strictly mentioned here. Yeah, we have to follow this one at any cost. Yep. So and weight has to be greater than or equal to 1 and less than or equal to 1000 as well. Yep. So and the output for each test case, if we cannot find the proper way to repair the roads, output we have to go with a no solution. We have already discussed this one. We have to go with the output no solution. Yep, in a line, right? Otherwise, output the minimum cost to repair the roads in a line. They have strictly mentioned. Yeah. So this is simple actually. Let me delete this one entirely. Yeah, this is fine. Now let's move on with the solution part actually. Yeah. So let's do one thing. Let's discuss the approach first. Let's see how we can implement the Steiner forest algorithm. So we'll be making use of the partition DP. I'm telling it first itself. So we'll be going with the Steiner forest algorithm along with the this one partition DP. Yep. So to solve this particular problem, let's see the approach. It's simple. Yep. if you remember the algorithm, all we have to do is we have to group the terminal edges and we have to take the minimum cost, right? Minimum cost. That's what we will be doing here as well. So we'll be making use of the this one partition DP just for the sake of intense optimization. Yeah, just remember this part. Just come here. Let me minimize this one. Algo part. Let me go to the problem part. Let's do one thing. Let's start writing the code step by step, right? So, or we haven't considered the approach, right? So let's consider the approach first, or let's discuss the approach part. So here for the approach, I have went with the same, this one, what do we call? Same input, the first input in the question, right? Fourth, we have 431, 4210, 319, as well as the 2310. So these are the edges with the this one. What do we call? Weights actually. They're strictly mentioned here. Meaning we have four houses here. So you can clearly see n equals to 4, right? So we have four houses. You can clearly see here. 1, 2, 3, 4. It starts from the 1. K, it starts from 1 to this one. K, right? So we have houses 4, 1 to K here. The highest number that we have is 4 within this one edges actually. So we have four houses, n equals 4, and we have three roads. You can clearly see we have three roads and we have K equals 1. So K equals 1 family, right? So this is fine. So family house is nothing but house 1. We'll be considering a house 1 and hiding house is nothing but the house 4. The highest one that we have is hiding house, nothing but the house 4. And the family house will be starting with the first house, nothing but house 1, right? So n equals 4, n equals 3, and n k equals 1 indicates 4 houses, 3 roads, as well as this one family. And family house is nothing but the house 1, and the hiding house is nothing but the house 4. And the broken roads that we have here is 4, 2, 3, 1, 2, 3. So this one 4, 2, 3, 1, 2, 3, right? So this one is nothing but here this is nothing but k equals 1, and this part, this is nothing but m, yeah, nothing but 3 roads, and this is nothing but this part is nothing but 4 is nothing but houses actually, yeah, or n actually, n or houses. Right here, houses, just for the reference, don't get confused here, right? So this is the input 4 to 2, 3 to 1, and 2 to 3 with a weight 10, 9, and 10 respectively. Yep, k equals 1 we have, they've strictly mentioned. So family house is house 1 and hiding house is house 4. Broken roads 4 to 3, 1 input 4 to 3, 1, as well as 2, 3. This part with the cost 10, 9, and 10 respectively. Cost or weight, however we call it, right? So in the question they have mentioned as cost itself. Let's go with the cost itself. Yep. So this is fine. As we have considered this one as this one graph actually, it's usually we'll call this one as weights. So this is nothing but cost. Cost is nothing but the weight, and the inputs are nothing but the broken roads. M is nothing but 4 to 2, 3 to 1, and 2 to 3, nothing but edges, right? Edges for the graph. What is our main goal here? So family at house 1 must reach the hiding house, this one 4, with the minimum repair cost accordingly with the question. Again, so we have discussed this one. So we have to, our main goal is to find the family at house 1, uh, this one, the total repair cost we have to find. So family at house 1 must reach the hiding house, nothing but the highest house, right? This one, it has to reach the hiding house 4 with a minimum repair cost, right? That's what we need to find, right? So this is the graph accordingly with the input actually. So 1 to 3 with a weight 9, 3 to 2 with a weight 10, and 2 to 4 with a weight 10 as well, right? So here family location is 1, this one, and hiding place is nothing but 4, this part. Yep. So this is fine. I insist you to pause the video and have a look into the graph, right? So yep. So I insist you to again pause the video and have a look into the graph, right? Again, family location is 1. I have already marked. Hiding place is nothing but 4. Yep. So this is fine. But next, let's move on with the first step. So possible paths from 1 to 4. So we have to go from 1 to 4, right? So possible paths are, we have to move towards the 3, then 3 to 2, then 2 to 4. Yeah, 1 to 3, 3 to 2, and 2 to 4. Cost would be 1 to 3. From 1 to 3, it's 9. From 3 to 2, it's 10. Yeah, and from 2 to 4, it's 10. Right? It would be 9 plus 10 plus 10. It would lead to 29. Yeah. So 9 plus 10 plus 10. So total is 29. So we will not will not stop here. We have to check for other paths as well if other paths exist, right? So we have to check for that as well. So there are no connections from 1 to 4. So the only valid path we have is 1 to 3, this one, 1 to 3, 3 to 2, and 2 to 4. This is the only valid path we have actually. So this is the valid route actually, 1 to 3, 3 to 2, 2 to 4. So as we do not have any valid route or valid path, total repair cost would lead to 9 plus 10 plus 10. This one itself, nothing but 29. So the output that we need to get is 29, right? So this is the approach that we will be going with accordingly with the this one, what do we call algorithm that we have written. Yep. So this is it for the approach part. It's very simple. Yeah. This is it for the approach part. We are done with the approach part. Next, let's do one thing. Let's try to articulate the same thing in the form of code. Yeah, let's try to articulate the same thing in the form of code. If we get the desired output, then we can discuss the complexities for the code that we have written. First, let's try to articulate the same thing, whatever we have discussed in the form of code. Let's do that. So let's continue with the problem part. First thing, we'll be making use of the, what do we call, a different utilities. So I'll just import java.util. So one second, let me type this one, util.start. We'll be making use of the different utilities, right? So this is fine. Within the main class, or the this one, peach blossom spring. So this is the question name actually. So this is fine. Let's do one thing. Let's go with some global variables, right? So I'll just go with static here. So I'll just go with final int. So let me go with the infinity. So I'll just go with 1, left shift 20. This is for the optimization purpose. We will be going with a bitmask DP. Yeah, we'll be making use of partition DP or the bitmask DP. So I'll just go with this one, left shift 20, or let me go with the left shift 28 for the optimization. So we'll be making use of it, right? So I'll just go with a static here, int n. So this is fine. This is nothing but the number of houses, and also we need the adjacency list, right? So we have to store the edges somewhere. So for that, we'll be making use of the list actually. So I'll just go with int here. So this is fine. Yep. I'll do one thing. Yeah, this is fine. I'll just go with the adjacency. So this is fine as well. Let me remove this p part. This is not necessary. Yeah. So I had mistyped. So now let's move on with the main method. So I'll just go with public static void main. Sorry. So this is fine. Within the main method, the first thing, so we can just make use of the scanner, right? So we don't have to go with the this one, as the constraints are not very tight. So we can just make use of the scanner instead of this one, buffer data and the print write out. So we have to go with the input output package as well for that. Yep. So I'll just go with the scanner here. Scanner. So let me go with the variable sc. So I'll just go with scanner system.in. So this is fine. The next step is nothing but we have to go with the number of test cases here. Number of test cases, I'll just go with t equals sc.nextInt. This part. Yep. So this is also fine. The next part is we have to process each test case. Nothing but I'll just go with a while here. While t, this one. Sorry. I'll just go with this one, while loop. So we have to read the number of houses first. So I'll just go with n equals sc dot nextInt. So this part. So we have to go with the number of roads as well. So I'll just go with m equals sc dot nextInt. So this is also fine. We have to go with the number of families as well. So I'll just go with the k equals sc dot nextInt. So this is also fine. And we have to initialize the adjacency so not the adjacency matrix. We have to initialize the adjacency list. So I'll just go with equals new list of n, right? So this one is fine. So we will be going with the n actually. It depends on the number of vertices, not this one edges. Right, so this part is not required. Let me remove this one. Yeah. Let's move on with the further things. So what are the things that we have considered here? Size and this is. Yep. Now let's do one thing. Let's create the empty neighbor list for each house. For that, I'll just go with for I equals 0. I'll just go with I less than n. Let me increment the I. So within the for loop, I'll just make use of the adjacency list, adjacency of I. So this one, let me make use of the array list here, right? So this is fine. Next step, so we have to read all the rows. For that, I'll just go with for here. Within the for loop, I'll just go with int e equals 0, e less than m. Then let me increment the e. So within the for loop, first thing we have to convert the houses to 0 index. So I'll just go with int u equals sc dot next int this part, and I'll just go with a next dot next int -1, and for the vertex v as well, right? So I'll do the same thing, next int -1. So this is fine. We have to repair the cost. So we have to find the repair total minimum cost itself, right? So I'll just go with int weight nothing but w equals sc dot next int. So -1 is not required for this. Anyways, now we have to add the bidirectional edge because we are dealing with the undirected graph. Yeah, we are dealing with the undirected graph. So we have to add the bidirectional edge. Suppose if we are having this one 0 to 1, we have to add 1 to 0 as well, right? So let's add the bidirectional edge. For that, I'll just write here in this adjacency of u. So I'll just go with the add here. So this one will be new int of what? So I'll just go with a v, comma w. Yep. So this is fine. What did I do? Yeah. This one I have closed here itself. So that is the reason we're getting error. Anyways, so let me close here. So let me do one thing. Let me copy the same thing. And let me change the names here. So I'll just go with v. This is fine. V dot add. So this one new, and so this one will be u, and this one will be w, right? So after adding the bidirectional edge, the first thing I'll just come out of this one entirely. Now we have to go with the total terminals, and that is nothing but equivalent to the families plus hiding houses. So I'll just go with the numt equals 2 into k actually, right? So this is fine. Yeah, so the next what we'll be doing, we have to go with the terminal nodes. So I'll just go with int term. So this one will be new int of numt. So this one. So this is fine. Next, we have to go with the families located at the houses, nothing but 0 to k minus 1, accordingly with the question. So I'll just go with the for loop here. So this one will be int I equals 0. I has to be less than k. I'll just increment the I within the for loop. Let me do one thing. Let me write it directly here itself. So this one will be term of I. Let me assign this one to the I. Yep. So I'll just go with a one more for loop because hiding houses are located at n minus k to n minus 1. Right. So I'll just go with one more for loop here. So this one will be int I equals 0. Again, I less than k. Let me increment the I. This time it would be so this one will be term of I'll just go with a k plus I. So I'll just assign this one to n minus k plus I. Yeah. So this is fine. Next, what we have to do, we are done with this part. Yeah. What happened here? Why this is screaming here? Variable I is already defined in the scope. Yeah. So let's move on with the further things. So this is fine. Let's do one thing. We have to compute the Steiner DP, right? So I'll just go with, let's do one thing. Let's go with a helper method, and then we can just make use of it within the main method actually. So let me do one thing. I'll just come here. So I'll just go with static here int. So this one will be, sorry, int. So this one will be Steiner DP. So I'll just go with the int numt. So this is also fine. Int, I'll just go with a term. Right, so this is fine. Within the Steiner DP, what I'll do, let's go with a DP array. So I'll just go with int. So let me go with the DP equals new int of 1. So let me go with 1 left shift numt. So this one, yeah. So this is fine. Numt and also the size n. Yeah. So this is fine. So we have to initialize with infinity. For that, I'll just go with a for loop. So this one will be int row of dp. So next what I'll do, I'll just go with arrays dot fill. This one is fine, arrays dot fill. Let me go with a row as well as I'll just this one initialize this one with a infinity. So this part. Yep. So this is fine. So next, let's go with a base case. We have successfully initialized with the infinity. Now let's go with a base case when when we have the single terminal only, meaning only one edge, right? Um, the front. So the two edges at the end of the graph, only one edge present, right? So for that case, I'll just go with for. This will be the base case actually. I'll just go with int I equals 0, I less than num t, and let me increment the I. So I'll just write here dp of 1 left shift I, and this one will be term of I. So let me assign this one to the 0. Yeah, this is fine. It's simple. Now we have to iterate subsets. For that, I'll just go with one more for loop. So this one will be int s equals 1, s less than, this has to be capital S. We have considered capital S, right? So s less than, I'll just go with 1 left shift num t. Yeah, so this is fine. Let me increment the s. So this is fine. Within the for loop, I'll just go with one more for loop here. We have to merge the smaller subsets, right? So for that, I'll just go with a for. Let me consider for the subsets, I'll just consider the variable sub equals s minus 1 here. So logical and this one s, and let me go with a subset. If it is greater than 0, then sub nothing but the subset equals, I'll just go with a sub minus 1 logical and so this one will be s. So this is fine. So within the for loop, what I'll be doing, so I'll just go with a form. So I'll just go with s XOR sub, right? So this s has to be capital, not the smaller one. Yes, XOR sub. So next, suppose if the sub, if it is less than the comp that we have considered the variable, so in that case we have to exit from there. So I'll just give continue. So we have to combine the trees. We have to combine the trees. For that, I'll just go with for int v equals 0, v less than n, and let me increment the v, right? So this is fine. I'll just go with v here, capital V, and again this one has to be capital V as well. Yep, so this is fine. Within the for loop, I'll just go with a simple if condition. If dp of sub sub into v, suppose if it is less than infinity, this one, yeah, I'll just go with this v has to be small actually. Anyways, if it is less than infinity, and also I'll just go with dp of comp, the variable that we have considered, into v. So if it is less than infinity, yeah, so this one will be small v. Yeah, if it is less than infinity, then I'll just go with dp of s into v. Yeah, so we have to consider the minimum, right? So I'll just go with here math.min. For this, I'll just go with, so this one, for this, we have to go with a small v itself, right? So why we are getting error here? Cannot read the symbol v. Within the for loop, we have considered big V. So I'll just go with small v here. Yeah. So this is fine. Now the error should be gone. So within the minimum, what we have to do, I'll just go with the dp of s into v, right? Comma dp of instead of sub v, I'll instead of comp v, I'll just go with a sub v, and finally all I'll do is I'll just go with a dp of comp here, right? So this one more I have to provide v. I completely forgot the v here, right? Quite obviously we'll get the error if we forget that. Next, I'll just come out of this one. So let's make use of the ditstra here, right? Let's make use of the ditstra to expand the tree, right? So I'll just go with int, so d equals dp of s. So this is fine. Yeah, dot, let me make use of the clone here. So this is fine. Next, I'll just go with a priority queue here. Distri uses priority queue itself, right? So I'll just go with a priority queue as the distri uses priority queue, right? So this is fine. PQ, new priority queue. So this is fine. So instead of this, let me change here. Not required. So here I'll just go with the comparator. So this one dot comparing. So will be yeah. Let's go with the comparing int itself, right? So a2. So you can just consider a, or you can just go with the x. The variable doesn't matter. So I'll just go with the x of 0. Yep. So this is fine. We are done with this part. Next, after considering the priority queue, we have to push all the nodes. I'll just go with a for loop. You have to know the Dijkstra's algorithm for this one, right? So let's do this one. We are just pushing we are pushing all the nodes to the priority queue. So I'll just go with, it's very simple if you know the Dijkstra actually. Yeah. So if you don't know the Dijkstra's algorithm itself, so please to go through the algorithm. It's present in the 150 algorithms playlist. Yeah. So this is fine. Now, what I'll do, v less than n. So I'll just increment the v. So this is fine. I'll just write the simple if condition here. So if, suppose if d of v, so if it is less than infinity, yeah, then what we have to do, I'll just go with pq dot add. So let me go with new int. Yep, new int. So this is fine. Let me go with d of v, yeah, and also v irrespectively, right? So this is also fine. Yeah, I'll just give the semicolon here. So this is fine. Let's move on with the Dijkstra's part. Yeah, let's move on with the Dijkstra's part, right? So let's go with the standardized while loop. So I'll just go with priority queue. When priority queue is not empty, then first thing we have to remove, right? So for that, we'll be making use of the poll. So this one current equals pq dot poll. So this is pure DFS, right? Sorry, BFS, right? So this is fine. If current of 0, if it is so not this one actually. Suppose 0, if it is greater than d of current of 1, right? So this one, yeah, d of current of 1. In that case, what we have to do? So in that case, I'll just give continue. So next, I'll just go with one more for loop here. So this is pure BFS. So I'll just go with a NB of adjacency of this one, current of 1, not 0. So this one will be 1. Let me change this one to 1. So within the for loop, what I'll do, I'll just go with the if condition. If d of current, so this one, current of 1, d of current of 1, then so I'll just go with plus this one, nb of 1. So this is also fine. b of nb of 0. So what did I do here? So we are going with the if condition, right? Current of 1 plus nb of 1. This is also correct. So if it is less than d of nb of 0, then what we'll be doing? So I'll just write within the if condition d of nb of 0. Yeah, d of nb of 0 is equivalent to d of current of 1 plus nb of 1. Yep, so this is correct. Next, I'll just we have to add this one value to the priority queue, right? So I'll just go with the new int here, new int. So within this one, I'll just mention nb of 0 comma nb of 0 twice actually. So 1 is not required. Let me mention 0 itself. Yeah. So this is fine. Let me format the code so that the code looks good. Yep. So we are left with only one thing. So I'll just come out of this one. So let me come out of this one here. So let me assign dp of s2 d. Yeah. So this is fine. And all we have to do is we have to return the dp. Yeah. So let me do one thing. I'll just return dp. Yep. So we are done with this particular part. Yep. So we are done with this particular part. Next, we have to go with the next permutation generation as well, right? So I had mentioned next permutation. Have we made use of the next permutation? No, right? So somewhere I have done something wrong. 1 second. So let me do one thing. I'll just cut this one over here, this one, and let me paste it over. Uh, this part. Yeah. So next, what I'll do? Hmm, what am I gonna do? Hmm, this is not required here. I believe was correct itself. It was in place. Anyways, so this is fine. DP, yeah. So let's do one thing. Let's move on with the further things. We need, or let's do one thing. Let's make use of the this one, Steiner DP within the main method. Yeah. So where we have left, I have completely forgotten actually. Just give me a second here. 1 second. So here we have added the bidirectional. These kind of things we have already done, right? So all we have to do is mm, we have to move on with the this one. We have to compute the Steiner DP. So I'll do one thing. So I'll just come here. So let me give int. So I'll just go with DP equals. Let me paste this one over here. Steiner DP, the method name, and let me pass the parameters. Nothing but numt as well as term. Right. So next, let's move on with the further things. We need to calculate minimum. So I'll just go with the min DP here. Min DP equals new int of instead of the size n. So this is not required, I believe. Rest of all, min DP, I'll just fill this one with a infinity. This is fine. And instead of the size n, as we are going with a bit masking, so I'll just go with a, so this one, one left shift numt. Yeah. So this is fine. Yep. Next, we have to find the minimum cost for each subset. For that, I'll just go with a for int s equals 0, s less than. So I'll just go with one left shift, this one numt, this one, and finally I'll just go with a s plus plus. Yeah. So this is fine. Let me go with simple for loop. So I'll just go with int v equals 0. So I'll just go with a v less than n. Let me go with v plus plus. Yeah. So this is also fine. The next step will be min dp of s. So this is also fine. I'll just go with the math.min of min dp. So this is fine. Min dp math.min of min dp of s. Remove this one. Min dp of s, ma dp of this one, s and v respectively. Yeah, dp of s and v respectively. So this v has to be small. So let me, yeah. So this is fine. We are done with this part. Yeah. Let me format the code so that the code looks good. Now let's move on with the further things. So I'll just do one thing. So we have to go with a permutation array for hiding the assignments. For that, I'll just go with the int. So let me go with the permutation. So this one will be new int of k. So this is also fine. Next, we have to initialize the permutation. For initializing the permutation, I'll just go with for loop. So I'll just go with the int I equals 0, I less than k. So let me increment the I. So this is fine. Then let me go with the permutation of I. So this one, let me assign this one with the I. So final answer, we have to store the final answer somewhere. Let me go with the resulting variable result, or I'll just go with the ANS here, right? So let me assign this one to initially infinity, or let me initialize this one with infinity. So we have to enumerate all the k permutations, right? So for that, I'll be making use of the do while loop here. So I'll just start with the do here. First thing, we will be making use of the DP over subsets of family pairs. So I'll just go with int. So this one will be forest DP. Yeah. So let me assign this one to new int of one left shift. Yeah. Yep. So this is fine. Next, I'll just go with a arrays.fill. So this one will be forest DP comma infinity. So this is also fine. Next, we have to go with the empty set cost, nothing but forest dp, this part, forest dp of 0, forest dp of 0. So let me assign this one to the 0. Yep, so this is also fine. Next, we have to iterate over all the subsets. For that, I'll just go with for int p equals 1. Let me go with p less than 1 left shift k. And finally, let's go with a p plus plus. Yeah, so this is fine. This for loop is fine. And we have to enumerate the subsets as well. Again, the nested loop, one more for loop here. Int q equals p, and q should be greater than 0, and q equals this one, q minus 1 logical and p actually. Yep, so this is also fine. So then within the for loop, we have to go with the terminal mask. Let's do one thing. So huge man. Anyways, where we have left. So enumerating subtrees we have right? Yeah, we have written the nested for loop. Now let's go with the terminal mask. So I'll just go with the int t mask. Let me assign this one to 0. Yeah. So and we have to build the terminal mask for the subset q. For that, I'll just go with a for loop. So this one will be int I equals 0, I less than k. Let me increment the I. So within the for loop, I'll just go with the if condition. So this one will be if. Let me go with q right shift I, logical and 1. Suppose if it is equivalent to 1, right? Suppose if it is equivalent to 1, then we have to add the family terminal. So I'll just go with a t mask here. T mask. So I'll just go with a logical r equals 1 left shift. This one, what do we call? 1 left shift I. Right. So this is fine. Simple to understand. So after adding the family terminal, we have to add the hiding terminal as well. For that, let me go with the t mask again here. So this one logical r equals the same thing, 1 left shift. So I'll just go with within the array we have to present, or yeah, let me go with the this one. Let me not go with array. So I'll just go with the permutation of I. With permutation of. So this is fine. Yep. So we have successfully added the hiding terminal. I got confused that whether we should add this one, a plus permutation of I within the parenthesis or the array. So this is fine. Now let me come out of this one entirely. So we have to go with a cost to connect these particular terminals, right? So I'll just go with the TC here equals min dp of, I'll just go with a t mask, right? So next we have to go with the remaining subset. I'll just go with the remaining rem here. So this one will be p to the this one x or q, right? So this is fine. Next we have to combine with the remaining dp. For that, I'll just write the simple if condition here. Tc, if it is less than infinity, and we have considered the variable forest dp, right? So this one forest dp of remaining rem. So this one, if it is less than infinity, yep. So then I'll just go with a forest dp, this part, yep, forest dp of p, yeah, p. I'll just go with math. We have to consider the minimum value, so I'll just go with a math.mun of forest dp of p, which is p here, not the remaining. So I'll just go with a p, comma. TC is correct. So here p we have to go with a capital P, right? Sorry, have considered the capital P here. So TC, let's concatenate the forest dp of remaining actually now. Forest dp of now let me pass the rem. So this is fine. Yep. So we are left with only one thing, nothing but suppose if what do we call? Suppose if q, if it is equivalent to 0, then we have to exit from there. So I'll just go with a break statement. Yeah, I'll just come out of this one entirely. Now we have to update the global answer. For that, what shall I do? We have considered the this one resulting variable as answer or the ANS. So I'll just go with a math.min here, right? So let me pass the resulting variable as well as forest dp again. Here this should be 1 left shift k minus 1. Yeah, k minus 1. This one we have to mention within the array, or this one we have to go with this one. I think uh, within the array I have to give parenthesis. Yeah, so this is fine. K minus 1. I have to close the array here, right? So this is fine. Yep. Next, let's go with the while, as we are making use of the do while. So I'll just pass the next permutation. For the next permutation, we haven't written the code at all. Yeah, for the next permutation, we haven't written the code at all. So we have to write the code for that. So 1 second. So here we'll be writing this one over here. This is fine. Let's look at it later. So first, let's do one thing. Let's move on with the helper method next permutation, right? So let's write that one quickly. So we have to generate the next permutation. For that, I'll just go with the static here. Let me go with a boolean, and I'll just go with the name next permutation. Yeah. So this one is fine. I'll just go with the int a, right? So this is fine. So within the next permutation method, first thing, I'll just go with I equals a dot length. Yeah, dot length minus 2. And the second one, I'll just go with a while condition here. So this one will be if I greater than or equal to 0, and let me go with a of I if it is greater than or equal to a of I plus 1. So then I'll just decrement the I. So this is also fine. So I'll just go with a simple if condition next. If suppose if I is less than 0, then what we have to do, we have to sort, right? So I'll just go with the arrays dot sort of a, and we have to return false, boolean value false. Next, I'll just come out of this one entirely. So let me assign j to a dot length minus 1. Yep. So this is fine, the final value. So then let's move on with a while loop again. So I'll just go with a while here. Yeah. So within the while loop, I'll just go with if a of j, suppose if it is less than or equal to a of I, then what we are going to do, let's decrement the j. So next, let me consider the temporary variable. Let me assign this one to a of I. So I'll just go with a of I. Let me assign this one to a of j, and finally a of j to temp. Yeah, a of j to temp. So this is fine. Next, let's move on with the further things. Let's move on with the for loop. So I'll just go with the for int l equals I plus 1. So this is fine. R equals a dot length. This is fine. A dot length minus 1. L less than R. So I'll just go with L plus plus comma R minus minus. Yeah. So within the for loop, what I'll do, temp, I'll just assign this one to a of L. So this is fine. A of left. So this one, let me assign this one to the a of right. So this is also fine. Finally, a of right, let me assign this one to the temp. Yep. So this is also fine. Finally, what I'll do, I'll just assign or I'll just return true. If everything goes well, we have to return true in that case. So let me return true. So this is it for the this one next permutation method. So let me copy this one entirely. Now let me make use of the next permutation here, right? So this is fine. And next permutation of permutation, right? We have the parameter permutation or PERM variable. So let me pass that one, or the parameter. Yeah. So next, what we have to do, we have to print the result. I'll just go with the S out as we are making use of the scanner here. So let's print the result if it is greater than the infinity, right? So if it is not greater than, suppose if it is greater than the infinity, then let's print. If everything goes well, then no solution, right? If it is greater than or equal to infinity, then we have to display no solution. Else, let's display answer, right? Answer variable. Let me pass the answer variable here. Nothing but the resulting variable. So this is it for the coding part. So I'll just format the code once. Yeah. So this is it for the code. We have made use of two helper methods here. One is Steiner DP, which is quite obviously required for the optimization, and we have implemented the Steiner DP. This one. We have made use of the partition DP actually, right? So yeah, partition DP mainly called as this one. Steiner forest algorithm. So we have made use of one more helper method, nothing but the next permutation. We have to generate the permutation. So we have made use of the next permutation, this one helper method. Now we are done with this part. Let's do one thing. Yeah, somewhere this one, what do we call, misplace the brackets, I believe. So anyways, so let me run this one. If everything goes well, this is fine. Let me run this one. Yeah, variable I is already defined in the method. So this one, we didn't debug at that point of time, right? So I have misplaced the bracket somewhere. So let's see. Let's check what we have done wrong. So let me do one thing. So as I misplaced the brackets, I'm getting this error, I believe. So let me do one thing. So yeah, this one I have to close here itself. Instead, let me do one thing. I'll just remove the bracket itself. Doesn't matter. Right. So I'll just remove the bracket, one more bracket here, right? Or else I would have closed the bracket there itself. Yeah. So let me, mm, yeah, let me rerun this one. I hope everything is correct. So yeah, let me rerun this one. So yeah, it's asking for the input, right? So let me enlarge this one so that this looks good. Just give me a second here. Yeah, let's come to the PDF part. Let me copy this one entirely. Once again, why this is not there. Yeah, let me copy this one entirely. Now we have to get the output 29 and 5 respectively, right? So let's check the same. I'll just give this one. Oh, this is not taking it all. 1 second, just give me a second here. Yeah, I'll just come to the question part here. So let me copy from this at least entirely. Let me copy from here. Let me remove this one and paste it over here. Yeah, this is fine. We are getting 29 and 5. So this is not showing correctly, but see here, this one in the, so this one you can, this is bright, right? So the output actually for the first input, we are getting 29, and for the second input, we are getting 5. So whatever the code that we have written works absolutely correct, right? So this one you can check in the Java compiler as well. So I just wanted to show you within the, as I have typed in the IntelliJ, so I just wanted to take the input and show you here itself, right? So this is fine. We are getting the desired output, right? So now let me do one thing. Let me copy this one entirely. So I'll just come to the question part here. So yeah, so I'll just hit the submit here. So let me paste this one over here. I need to make certain changes. So this is just for the IntelliJ. Let me remove this one, and public is not required. So I'll just go with a class, and while submitting in this one, we have to go with the name main, right? So this is fine. Let me do one thing. Yeah, if everything goes well, we have to get the correct output. Let's see. Let me hit the submit button here. Time limit exceeded. Okay, 1 second. We have done something wrong. Let's see what we have done wrong. So what mistake I have done here is, so see here, within the Steiner DP, so we have went with the distra relaxation, right? We have made use of the distra actually. So distra uses priority queue, and here I have mentioned only NB of 0 and NB of 0. So we have to go with the distance of distance as well as node. We are just going with a node and node respectively. So this messes the this one actually ordering within the priority queue. That is the reason we are getting. I believe that is the reason we are getting this one TLE. So I'll just change this one over here, or I would have directly changed there itself. So let me come here. So I'll just go with this one here. Yeah, I'll just go with what shall I go with? So let me go with B of NB. So let me close this array again here, right? or we have to close the array here itself. P of nb of 0. Let me close this one, and we have nb of 0, right? So this is fine. Yep. Now we have to get the correct, correct solution. This one, it has to get passed, actually all the test cases has to get passed. So now we have considered destination as well as the node instead of the two nodes and nodes, right? Respectively. So I'll just copy the same thing again. So let me come here. So again, let me hit the submit. So let me paste it over here, and this time let me remove this one. This is not required, and let me remove the public. So this is also not required. Instead of this, let me go with the main, capital M or small m, it doesn't matter anyways. So I'll just go with the submit button. So this time it has to work. Let's see. Let's see. Yeah, this time you can clearly see here this got accepted, right? 2890 milliseconds. Actually 3 seconds is what they have given in the question. So it got passed almost, right? So this is fine. Whatever the code that we have written works absolutely correct. So that was wrong actually. Here within the dist here instead of the destination distance as well as the node, I have went with a node and node respectively within the adding. So this messes up again. This messes up the priority queue ordering. So it will give TLE quite obviously, right? So now we are getting accepted, right? So whatever the code that we have written works absolutely correct. So now we are done with the algorithm, right? Steiner forest algorithm, and we have got the opportunity to implement the same algorithm within this particular method, within this particular problem, right? So the problem name peach blossom spring. Yep, we have successfully implemented the this one Steiner forest algorithm with the partition DP, right? So this is it for the algo. Right? Next, what we'll be doing? Just give me a second here. Yep. Next, we will be discussing on the this one matroid intersection algorithm. Yep. So I hope whatever the algorithm that we discussed today, nothing but the Steiner forest algorithm is completely clear, right? So for now, this is it. Thanks for watching, guys.